Welcome to Neural Intel. Today, we're doing a deep dive into some really interesting technical developments in AI and ML.
We are. There's this new framework, R1 Searcher plus D. It's definitely worth looking at.
Exactly. R1 Searcher plus E. Think of it as a potential upgrade for how large language models, LLMs, access and use knowledge dynamically.
And for you listening, understanding this framework gives you a peek at, the cutting edge, how researchers are trying to make these models more reliable.
Right, and less prone to making things up, those hallucinations we hear about.
Mm.
So our goal today is really to unpack the technical side of R1 Searcher plus E, how it works, what the implications might be, and as always, we're keeping the focus strictly on the tech.
Sounds good.
Okay, so let's start there. Why do these models, which are trained on so much data, sometimes get facts wrong or, well, hallucinate?
Yeah, that's the core issue, isn't it? It boils down to the static knowledge problem.
Yeah.
LLMs know a lot, but it's all based on the data they were trained on up to a certain point.
So that knowledge is frozen in time, essentially.
Pretty much. If information is newer than their training cutoff, or just wasn't well represented in the training data, they might struggle.
And that's when they might just invent an answer.
Exactly. Especially for factual questions or open-ended tasks that need current info. They fill in the gaps, sometimes incorrectly.
Okay. Now, people have tried to fix this. Retrieval augmented generation, or AGRE, comes up a lot.
Yes, RV is definitely a popular approach. The basic idea is simple. Let the LLM look things up in an external source, like a database or the web, before answering.
Like giving it search engine access. Makes
Mhm.
sense. But you hinted earlier that current AGRE methods aren't perfect. What are the shortcomings?
Well, there are a few. First, cost. Constantly hitting external databases or APIs can get expensive, computationally speaking.
Right.
Second, generalization isn't always great. They might work well on tasks similar to their training, but struggle with new types of questions. And maybe most importantly, for R1 Searcher plus data, many ArcGIS systems don't make good use of the model's own internal knowledge. They might search even when they kind of already know the answer.
Ah, okay, so they're not very good at judging, do I know this or do I need to look it up?
Precisely. They can be a bit trigger-happy with the search function.
And this is the gap R1 Searcher plus is designed to fill. How does it approach it differently?
It uses a novel framework specifically designed to train LLMs to adaptively switch between using internal knowledge and external search. The key is this two-stage training strategy.
2 stages. Okay, tell me about stage 1.
Stage one is the SFT cold start.
Hmm.
SFT is supervised fine-tuning. Here, the main goal is teaching the model the format for knowledge seeking.
The format.
Yeah, using special tokens, like internal means I'm using my own knowledge now. External means, okay, time to search.
Hmm.
And document is for incorporating the info found.
So it's like learning the punctuation for thinking and searching. And what's reject sampling doing here?
That's just a way to make sure the training data for this first stage is really clean. They generate examples and only keep the ones that perfectly follow that internal-external document format. Quality control, basically.
Gotcha.
Equation 2 in the paper shows the loss function for this. It focuses on getting those special tokens right. Think of it as just focusing on the structure at this point.
Okay, so stage 1 sets the structural rules. What about stage 2?
Stage 2 is RL for dynamic knowledge acquisition, using reinforcement learning. This is where the model learns when to use internal knowledge versus when to trigger that external search token.
RL, so rewards and penalties guiding its decisions.
Exactly. The aim is to reward the model for using its internal knowledge if it's confident and correct, and only reward searching when it's genuinely necessary, like when it's uncertain.
That sounds way more efficient.
That's the idea. And there's another piece, a memorization mechanism.
Memorization, so it learns from the searches.
Yes. It's designed so the model doesn't just use retrieved info for the current answer, but it can actually learn from it, update its own internal knowledge. It gets smarter over time from its searches.
Wow, okay. So it's not just looking things up, it's integrating what it finds. That's quite different. Let's dig into the mechanics a bit. How does that reasoning process with the tokens actually play out?
So, as the model generates its response, it's constantly evaluating, do I know the next piece of info? If yes, it wraps its internally generated knowledge in internal tags.
Okay.
If it hits a point where it thinks, I need to check this, or I don't know this, it generates external pat followed by a query. The system fetches documents, and those get inserted using document.
A dynamic back and forth. And the RL part uses reinforce plus new. Any reason for that specific algorithm?
Yeah, Reinforce++ is known for being pretty stable, which helps in complex training. Plus, it doesn't need a separate critic model like some other RL methods, which can simplify things a bit.
Simpler is often better.
And they do something clever with the math. Since the retrieved documents are like observations from the outside world, not generated by the model itself, they mask them out when calculating the RL loss. Equation 1 shows this. It helps the model focus on learning when to search, not on predicting the document content.
Right, you don't want it penalized for the content of a Wikipedia page it just retrieved. Makes sense. Okay, let's talk rewards. How do they actually encourage using internal knowledge? It sounds like a complex reward setup.
It is, yeah. It's a composite reward, multiple parts working together. First is the format reward. Equation 3 covers this. It's strict.
Strict how?
The model has to put search queries inside external tags. It can't just make up document content. It has to actually retrieve it. And the final answer needs to be in curly braces. Get the format right, reward is 0. Get it wrong, penalty is -2.
Okay, enforces the rules. What's next?
Then there's the answer reward,
Yeah.
equation 4. This checks if the actual correct answer is present in the model's final response. They use cover exact match, CEM, for this.
CE.
Yeah, it just checks if the exact answer string is found. And crucially, they limit the answer length to 10 words.
Ah, why the length limit?
To stop reward hacking. You don't want the model just spitting out a huge paragraph, hoping the answer's in there somewhere. Keep it concise. Correct answer, reward of 1. Incorrect, 0.
Oh, smart. Prevents gaming the system. And the third part was the group reward. How does that work?
Right, equations 5 and 6. This one's about efficiency and consistency. It looks at multiple attempts by the model to answer the same question.
Yeah, okay.
If the number of times it calls the search engine varies wildly across those attempts, it gets penalized. The idea is to encourage it to find a consistent, hopefully low search path to the answer. Lower variance in search counts means a better reward. They use standard deviation for this, with a clipping factor to keep it stable.
So it encourages finding an efficient and reliable strategy, not just stumbling onto the answer differently each time.
Exactly. Consistency matters.
And the total reward is just all these added up.
Yep. Equation 7 shows the final reward is format plus answer plus group rewards.
Okay, clear picture on the rewards. Now, back to that memorization part. How does it actually take external info and, absorb it?
Good question. They describe it as rewriting the retrieved information to match the model's internal knowledge style.
Rewriting.
Yeah. First, they train a separate, smaller model just for this rewriting task. It learns to take external document info and phrase it like the main model would if it knew it internally.
Okay, a translation step.
Kind of. Then, during the main RL training, whenever the R1 searcher ++ model gets an answer right using external search, they take the retrieved documents, run them through the rewriter, and create a sort of ideal internal knowledge version of the reasoning path.
I see.
These rewritten search-free reasoning paths are collected into a memorization dataset, T, and the main model is then also trained to predict these paths directly. Equation 8 gives the loss function for this memorization part, I'll remember.
So it's learning, okay, this is how I would have reasoned if I'd known this all along.
Pretty much. And the final overall training objective, shown in equation 9, LA, combines the RL loss for deciding when to search and this memorization loss balanced by a weight.
So it's learning to search smarter and learning from the searches simultaneously.
That's the core idea. A cycle of searching, learning, and needing to search less over time.
Okay, fascinating setup. But the big question, does it work? What did the experiments show?
They tested it quite thoroughly, used datasets like Hotpot QA, 2Wiki Multi-Hop QA, Music, and Bamboogle. Some were in-domain, meaning similar to training data, others out of domain to test generalization.
And the metrics, how did they measure success?
Standard F1 score for answer accuracy, measuring word overlap, and also LLM as judge, last J, using GPT-4o Mini to provide a more holistic quality score.
Okay, the results. Did R1 Searcher ++ actually perform better?
Yes, significantly. Table 1 in the paper lays it out. Across the multi-hop QA benchmarks, R1 Searcher ++ outperformed the baselines, including other RL methods like their previous R1 Searcher and Search R1, and even tree search methods like CR Planner.
How much better?
They reported gains of up to 4.3% over the prior R1 Searcher on the combined test sets, which, in this field, is a pretty solid improvement.
That is noticeable. What about the search efficiency? Did it actually make fewer calls to the external knowledge source?
Absolutely. That was a major finding. Compared to the vanilla RL approaches, R1 Searcher ++ cut down the average number of retrieval calls substantially. about 30% fewer than R1 Searcher and over 50% fewer than Search R1.
Wow, cutting searches by half compared to one baseline. That's huge for efficiency.
Definitely. It really backs up the claim that it's learning to balance internal versus external knowledge better. Less searching means faster answers and lower computational cost.
And how does it handle the out-of-domain tests, the completely new stuff?
It generalized surprisingly well, especially considering it wasn't trained on a massive amount of data. Performance on music and Bamboogle held up strong, suggesting it learned a robust strategy, not just memorizing training examples.
That's promising for real-world use. Did they do an ablation study, taking parts away to see what happens?
They did. Table 2 shows that. They removed components one by one. The SFT cold start, the RL stage, the group reward, the memorization, and performance dropped in each case,
Yeah.
sometimes significantly. Removing the RL stage entirely, for instance, really hurt accuracy. Taking out memorization also impacted both accuracy and search count. It shows that all those pieces we discussed actually contribute to the final result.
Good to see the components are all pulling their weight. What about testing it with a real search engine, not just a static database?
Yep, they did that too. Table 3 shows results using the Google API on Bamboogle and Frames datasets.
Still good?
So good. R1 Searcher plus outperformed the others, even when dealing with the messiness of live web search results. And it still kept its retrieval count relatively low. That's a strong signal for practical potential.
Very important test. How do they analyze the learning part, the knowledge acquisition?
They looked at retrieval counts versus accuracy in Table 4. R1 Searcher consistently used the fewest searches on average, whether it got the answer right or wrong, while still getting more answers right overall.
So it's more confident about when not to search, even if it sometimes gets it wrong?
Seems that way. It's more discerning. And Figure 3 is interesting too. It shows how rewards went up and search counts went down during RL training for R1 Searcher plus TELF, much more effectively than for the baseline R1 Searcher, which relied heavily on search throughout.
So the training curves visually support the idea that it's learning to be more self-reliant?
Exactly. And they included a case study, Figure 2.
Right, comparing the reasoning.
Yeah. On a sample question, the basic model just got it wrong internally. Search R1 found the answer but searched like 5 times.
Right.
R1 Searcher broke it down, searched once for a specific fact it didn't know when a bank was founded, used internal knowledge for another part, who was president in 1812, and got the right answer efficiently.
That really illustrates the dynamics switching nicely.
Okay, every study has limits. What do they acknowledge?
Mainly resource constraints. They used a static Wikipedia dump for most training retrieval, not a live search engine, because that's computationally demanding.
Okay.
And the main model they tested was 7 billion parameters. Big, but not the absolute state-of-the-art largest models out there.
So, potential for even better results with more compute, maybe a live search engine during training, and bigger models.
That's what they suggest, yeah. Integrating a real search engine during training and scaling up are their stated next steps.
Right. Okay, let's try and summarize the key takeaway from this deep dive on R1 Searcher plus B. What should listeners remember?
I think the main point is that R1 Searcher offers a more sophisticated way to train LLMs. It's about teaching them to skillfully blend their internal knowledge with targeted external searches, rather than just relying too heavily on one or the other.
So it's about intelligent knowledge management, not just raw retrieval. And that 2-stage training plus the reward and memorization seem key. Definitely. The SFT stage sets the structure. The RL stage teaches the dynamic decision-making. The rewards guide, that learning towards efficiency and memorization, helps it improve over time. It's a well-thought-out system.
And the potential benefit is more accurate, more efficient, and ultimately more reliable LLMs for complex tasks.
That's the hope. And the results so far look promising in that direction. More robust AI for knowledge-intensive work.
Which brings up a final thought. They mention the limitation of using static data during training. It makes you wonder, how much further could this go if models like this were trained with access to real-time, constantly changing information streams right from the start?
Yeah.
How might that continuous dynamic learning change their capabilities?
That's a really interesting question for the future. Definitely something to think about.
Indeed. Well, that wraps up our look at R1 Searcher plus Abstractor. Remember, if you want to keep up with the latest in AI and ML research, check out the Neural Intel webpage links in the bio. Thanks for tuning in.
Thanks, everyone.